this morning somebody told me that it was a very good advice. That if you go on the stage and you feel you have a bit of anxiety, you're supposed to tell the audience about it. Well, I don't have any anxiety. I have a stage fright. Yeah, so, and the same person gave me an advice, ask audience to give a bit of support. So if you could just give me a bit of support. Thank you very much. The same person just maybe half an hour ago did balance my chakras, so I'm totally fine. I'm ready to talk about regenerative medicine and stem cells and cell therapy. And talking about, touching this topic, I begin to suspect that Jim and Bernie, when they were creating the People Unlimited and the Coalition of Radical Life Extension, and Bill Falloon, for the matter of fact, probably when he was creating the life extension, they adopted some of the ideas from the ancient Romans. And we know that ancient Romans believed that, it was more than 2,000 years ago, that age itself is a disease, and we have to fight aging as we do fight the disease, and that's what the Cicero said. And basically, that's what the Coalition of Life Extension is doing, and the Radical Life Extension and the People Unlimited are doing as well. And now we know that, and it's scientifically proven that age itself is a single major factor of a huge number of age-related diseases. And in principle, if we understood of keeping the mechanisms and things repaired, we could keep things going indefinitely. And talking about this matter and keeping things repaired, what comes to my mind is a very lovely couple who are our patients in our German hospital since 1988. And since those days until 2018, when I saw them last time, they had about 16 or 18 sessions of cell therapy done, in a span of 30 years. A very lovely couple, a gentleman and his wife. Wife was 25 years younger than him, and she was 72, and the guy was 97. So that's how you can keep things repaired. And we know now that mammalian cell, the aging of the mammalian cell can be delayed, can be reversed with genetic, dietary, pharmacological, and biological and biotechnological approaches. And the biotechnological approach is exactly what I'm going to talk about. And why should we even bother about age? And why should we care about our aging population? Well, because from 2015 to 2050, and that's the data from United Nations, the population, the amount of people who are older than 85 years old is going to triple. And we are definitely a tremendously aging population. And unfortunately, medicine made us live longer, but it did not make us live better. And if you take, on average, in the United States, for example, people who are older than 65 years old, about at least 60% of them have one chronic age-related degenerative disease, and 90% have one disease, and 60% have more than two chronic age-related degenerative diseases. And the list of these diseases is way longer than is on this slide. And probably we're going to discover new and new diseases which are also dependent on the age, and we do that day by day. So please allow me to introduce the iceberg analogy. And what we see on the top of the iceberg, what is visible, are the clinical manifestations. And that's what conventional or traditional medicine is usually approaching. So they treat symptoms. And what is submerged beneath the water and what we can't see is the myriads of those cellular pathological mechanisms that other speakers were talking about today. And they actually cause those age-related diseases. And unfortunately, conventional medicine addresses only to the visible part of the iceberg. And it's sort of, it's a delusion, because the definition of the delusion is when you try to apply the same actions and expect a different outcome. So what we are interested in biological regenerative medicine is what is submerged underwater. And it's something that was talked about today and something that Aubrey de Grey calls 7 deadly things, but in other publications, other authors, they call it 7 pillars of aging. And it's a disruption of the metabolism, it's a macromolecular damage, it's a disruption of the epigenetic status, it's a low-grade chronic inflammation, it's impaired adaptation to stress, impaired proteostasis, and impaired regenerative potential of the tissues because we do deplete our stem cells and progenitor cells as we age. But lucky for us, we have figured out some of the mechanisms, and other speakers are talking about it, and we'll talk about it tomorrow and day after tomorrow. So there are some proven biological mechanisms that can help us to slow down those pathological processes and reverse them to a certain extent. And in our practice, we do use all of the mentioned above, what you see on this slide, and it gives quite good results. But what turns out that it's not always, it's not enough. And since 1881, we know that, and that was said by August Weismann, who is a very famous cellular biologist from Germany, from Freiburg University. He said that death takes place because a worn-out tissues cannot forever renew itself, and because a capacity to increase by means of cell division is not everlasting but finite. So we know that all tissues, they consist of the cells and extracellular matrix. And when we develop various degenerative diseases, we have either a premature death or senescence or malfunction of the cells, and we have disorganization of the extracellular matrix. And again, lucky for us, we have figured out that these processes are reversible, and it's called tissue remodeling. So we just have to find the ways how exactly to do that. So basically, we are left with two problems, two questions to solve here. The first one, we have to battle and fight the 7 pillars of aging. And the second question to solve is how to repair and regenerate tissues which have already been damaged, which have already started degenerating. And cell therapy at this point, and stem cells as one of the examples of cell therapy, looks like one of the most potent and plausible options in regenerative medicine to regenerate our tissues. So in the end, it's very important that the patient has to be absolutely motivated. They have to understand what exactly is going on with them. So it's a mind-body reprogramming. And then you can proceed with the tissue remodeling and cell reprogramming via the personalized medicine. Before we talk about mechanism of action and how to use stem cells, let's talk a bit about its safety, yeah? Because in medicine, everything starts with the safety trials. So in spite of all available data about the safety of different types of the cell therapy, different cell therapy products, and the stem cells, we have decided, and we've done our own survey, and we have employed a third party, which is a medical statistic agency, which is doing clinical trials and statistical medical evaluation in Germany. And they've done analysis. They took patients which are treated in our hospital. It's 186 patients from 22 countries. And they followed them up before, during, and after the treatment for at least 1 year after the treatment. They found out that there were no major adverse reactions. There were no complications. There were some mild transitory allergic reaction in about 2% of the cases. And generally, about 98% of the patients had improvement. And about 97% have the desire to come back and repeat this treatment sometime in future. So we know it's quite safe. Let's see how it works. And it's something that Aubrey de Grey also talked about today. And it's a normal biological process. It's a result of metabolism. As a result of our metabolic activity in our cells, in our tissues, we produce the senescence-associated secretory phenotype. It's just a collective secretome of different biologically active substances which do have beneficial, we actually do benefit from them in the early stage. Yeah? For example, they're beneficial in terms of fetal and embryonic development, in terms of tissue regeneration, wound healing, and even tumor suppression. But when the volume, the level of that signal, the expression of those biologically active substances really goes overboard, it starts causing the detrimental effects, and in a form of tissue degeneration, it causes chronic inflammation, and even the tumor promotion. And that all does contribute to the aging process and results in the 7 pillars of aging, ultimately. And lucky for us, we have found out that apart from other therapeutic modalities that we were talking about earlier, cell therapy and the stem cells, they sort of have a very synergetic effect. Okay, so they do influence in a very good, positive way all the 7 mechanisms of aging. But apart from that, and that is what commonly is accepted, Stem cells, they have their own solid ways of, and mechanisms of action. The first one is the homing effect. The homing can be either local, if, for example, you treat the cartilage and you implant cartilage cells directly into the joint, or it can be a distal homing, when you systemically administer stem cells, and then with the migration, with the further signaling, they will settle down in the tissues where they belong to. They will further proliferate there, and they will complete their differentiation. While doing that, cells will excrete a huge amount of various soluble factors, growth factors, cytokines, interleukins, and so on, and that is known as the paracrine effect. The paracrine effect is a very strong positive effect for the patient's own tissues in terms of stimulating the regenerative potential and also the differentiation and the proliferation of the patient's own stem cells, which we have in our body in practically in all tissues with exception of a few. And in the same time, stem cells have a very strong anti-inflammatory effect, and that's very important for MSCs. They excrete prostaglandins and the nitric oxide and the interleukins. They stimulate immune cells, so they reduce systemic inflammation. They have the immunomodulatory effect, which is also great. We also are interested whether stem cell therapy has got any direct influence on the mitochondrial function. And we have run some tests, and we have found out that before treatment, most of the patients who present us with various age-related degenerative disorders, they have impaired mitochondrial function. We see that with the lower levels of the humanin. It's one of the mitochondrial peptides, and the small humanin-like peptides as well. And after treatment, as fast as after 8 weeks after treatment, we see these parameters being normalized. The same goes to the antioxidant system, like the reduced glutathione assay, which was reduced, suppressed in patients before treatment, and it reaches the suboptimal levels after treatment. The superoxide dismutase and the catalase, which are very strong indicators for the antioxidative protective system, are also being normalized after these treatment protocols. And one of the ways how you can prove the actual anti-aging effect is by checking the biological clock, and that is done by the checking the patient's global methylation level, so the epigenetic status. For some time, we have been randomly doing that for some of the patients, those who are above 55 years old and up to the age of 75 years old, and we have found out that most of them, they have their biological age older than their chronological age. And after the 6 months of this treatment protocol involving the stem cells and the cell therapy, we have found out that most of the patients, they have a very good response and the reduction of the biological age. But because this study was not standardized and we use different labs, so the data is quite diverse, so it's on average from 4 to 9 years, that's age reduction that we have received. So for us to have a better understanding about it, we're going to run a proper clinical trial with one particular laboratory, and we're going to find out what is the exact amount of years that we can reduce with the stem cell therapy treatment. Now, what are the types of the stem cells that are used? The most frequently used type is the MSCs, the mesenchymal stromal cells, and this is probably the easiest type of the cells that can be procured and derived. You can take it from the umbilical cord, from the patient's own fat tissue, the adipose derived, or the bone marrow. But the problem with these cells is that they are great, and then we use them in our practice. We use the autologous cell therapy, we use the allogeneic, the umbilical cord blood, everything. But there is one problem with the MSCs, is that they have quite a limited differentiative potential. They can differentiate only into 7 types of the cells, and they create only or repair only 7 types of tissues, which are mentioned here, plus the blood cells. Plus, on top of that, if you infuse them intravenously, quite a large number, is about 99% of them are trapped in the lung, and they don't really disseminate in the organs which we want to regenerate. So it explains why quite often the outcomes are not as great as they expected, and the effects, the positive effects, are quite short-term. So if MSCs can repair 7 types of tissues, how about the rest 270? Because we have about 270 types of cells in our body, and MSCs are only responsible for the 7 of them. So how to repair the rest of the tissues. And the answer for that is in the precursor, also known as the progenitor cells. And these are the lineage-restricted cells which are absolutely committed on their pathway of differentiation. And probably this is the golden standard, and the cells which can actually deliver us a proper solid tissue repair. So we're moving away from the pluripotent cells. Nobody is using embryonic cells anymore for the past 20 years. And we're slowly moving away from the multipotent cells towards the unipotent cells, which are tissue-specific cells. If you compare the MSCs and the progenitor cells, it's like a shotgun and a rifle. So when you administer MSCs to the patient, it does have a wonderful general anti-inflammatory effect. The patients will have better, they will feel better, and that definitely there are benefits. And we do use that as well in our practice as the first step, just to prepare the patient's biological terrain to receive progenitor stem cells, which are the sniper rifle. So with the precursor stem cells, you can actually do the targeted, very precise tissue repair. And that's how these little heroes look like, with the different types of the stain. That's how the neurons look like with the nuke blue stain. And that's how the pancreatic cells, precursor pancreatic cells look like, with a different type of a staining. These are the connective tissue, the mesenchymal cells, and the neural cells with the fluorescent microscopy. So let's talk about clinical application. Historically, it's not something new. And how many of you have heard of the Carl Gustav Groth? Probably nobody, yep. And now late, but in 1994, he was one of the first people who did a xenogenic transplantation of islet pancreatic cells to his patients in Sweden in Karolinska University. And the results were so great that some of the patients were able to excrete insulin for as long as 300 days, for almost a year. And that was done to patients with the diabetes type 1. For your information, he was not the only person, because the other doctors and other researchers, they've done human clinical trials in other countries like Switzerland, Czech Republic, Poland, New Zealand, and all, and it was going until 2010s. And it was a long-term follow-up, 4 to 5 years, even up to 7 years. And with the xenogenic cell transplantation of the pancreatic islet cells, they were able to get a stable control of the glucose level without exogenous insulin being administered to patients from about 150 days to 300 days. In some of the cases, some of the patients were under control for as long as up to 4 years. Chronic liver disease. We do not wait for the disease to reach the final stage, and the patient would be doomed for the whole organ transplant. With hepatocyte transplantation, you can actually postpone the disease or even reverse that completely. And no matter whether it's hepatitis B or C associated or non-associated, alcoholic or non-alcoholic chronic liver disease, it is quite reversible. And it is very easily well tolerated by patients. There's probably no adverse reactions, and you can do hepatocyte transplantation practically as often as you wish. You can do it every 3 months, every 4 months, and keep the patient well. The only thing that we need to do now is just to get more data. We need more researchers and more clinical centers to do this kind of work, because the interest towards the hepatocyte transplantation is definitely there. It's increasing for the past 10 years. Chronic kidney disease, otherwise from point of view of conventional medicine, is practically incurable disease, because biologically Homo sapiens does not have ability, a capacity to regenerate our kidneys, because we exhaust the pool of renal kidney precursor stem cells about 2 to 4 weeks before we're born. So when we're born with a fixed amount of kidney cells, with a fixed amount of neurons, and we have no biological ability to rebuild it. So the only way how to slow down or reverse CKD is, again, by the use of the fetal precursor renal cells. And we have shown that if you catch the patient in an intermediate stage before it's too late and the patient hits the end-stage renal failure, you can actually downstage them. In a stage 3B, you can downstage them in about 66% of cases, and in stage 3A in 78%, and keep them stable for at least a year. Probably after 1 or 2 years, you can repeat this therapy again, and the patient will never need dialysis and kidney transplant in life. Cardiac repair. Of course, there are attempts to infuse MSCs and all, but it doesn't really work that well. If you just rely on stimulating of a natural intrinsic cardiac cell turnover, it's also hopeless because we renew about 0.4% of our heart cells in a year. So biologically, we have no ability, no capacity to regenerate our heart without external intervention. And the heart is a very stubborn organ. Even if you directly infuse MSCs in a heart, they are washed off very, very fast, within 2 to 4 minutes. And after about 5 to 7 minutes, you have less than 5% of the cells that you infuse stay in the heart, and they're all disseminated all over the body. And another problem is that the more time it passes from the acute myocardial infarction to the moment of treatment, the less is the capacity of the heart to retain those cells. So again, you can treat that with precursor cardiac myocytes. So we have found out that with the precursor cardiac myocytes, we can increase ejection fraction from in between 13 to 20%, and that can be done as fast as within 3 months. The stable results stay for up to 2 years. The xenotransplantation in chronic age-related neurodegenerative disorders, whether it's dementia, various forms of dementia, Alzheimer's, Parkinsons, and all, is now considered to be the golden standard, because now we do understand the nature of the disease. And by transplanting the cells which are responsible for the production of synthesis of dopamine, for example, we can keep Parkinson under control. Initial data is about 20 years ago that was about only 30% beneficial outcomes, but with the improved cell prescription, it's about 70–75%. And also along the way, we have found out that it's very safe, and patients almost have no negative immune response to that. It's one of the first clinical, probably the first clinical trial on xenogenic transplantation Parkinson patient was done on 12 patients 20 years ago. One of the patients has passed away 8 months after treatment to the cause which was not related to the cell transplantation. He died because of the acute pulmonary embolism. But because that person was a subject for the clinical trial, he went for the postmortem, and they found out that 7 months after transplantation, he had the xenogenic neurons survive in the brain, and not only survive, produce dopamine, and this patient was actually quite doing well in terms of the Parkinson's disease. And they also found that transplanted cells were in a very close connection with the patient's own cells. And one of the cases that we had about 10 years ago was the 82-year-old person with Alzheimer's disease, and also he had the cardiomyopathy, and he was treated by stem cells, and this is 4 years after that. The person who was forgetting where he lives, his address, and where his home is, about every second time when he was stepping out of the house, 4 years after stem cell treatment, was so well that he started traveling all over the world, and he was sending us these pictures from the places that he has visited. We also found out that it is possible to help those patients with neurodegenerative disorders which also have the impaired pineal gland, and in medicine it's called as sundowning. You know, we know that patients with Alzheimer's disease and other forms of dementia, during the evening and night time, the symptoms are getting much worse and all. They also have tremendous horrible sleep disorders, and with the pineal site transplantation and the pineal specific peptides, this is possible to be reversed. And we have published that paper last year. So I'm almost done here. And the future strategies, deliberately I just put the multiple dots there. The future strategies is such that, and it's something that we're working on now, is that we are creating new protocols which will combine different types of the cell therapy and different types of the stem cells. And if somebody will hear this and steal this idea, please do this. You know, you're more than welcome if any practitioners would decide to adopt this idea, because we want really to really propagate it and all over the world and prove scientifically that it's working. So the first step would be the use of the MSCs, and it will just prepare the patient's biological terrain, reduce the level of systemic implantation, and then within 2 to 3 days after that, you can do the targeted cell therapy to repair targeted organs and tissues, and that can be done with the fetal precursor or the progenitor stem cells. And after that, there's a proper protocol. It's about 2 to 4 months of the follow-up with the organ-specific or the tissue-specific peptides. And that, of course, is done together with taking into consideration and treating and fighting all those 7 pillars of aging that we're talking about. So how to succeed practically first of all, every patient has to be examined and investigated properly with all the biological markers of aging, genetic and epigenetic tests as much as possible, because the practitioner has to understand 100% what is going on the cellular level with the patient. And then do not neglect minor things. And you can do 9 things right, 1 thing wrong, and it will spoil the soup. There are no minor things. And if the treatment has to start with a lifestyle changes, with the calorie restriction, it has to start with that because it is scientifically proven, and the patients have to understand that, and it's doctor's duty to explain properly to them. And another thing, last thing, take-home message, please remember that stem cells is not a magic pill. There's no panacea, probably it doesn't exist. But what we should do is to reduce the uncertainty about the stem cells. And to reduce the uncertainty around the stem cells, we just need more clinical trial, we need more expertise, we need to try doing it more, involve more researchers in that, and of course get more experience. And that is the way to succeed. Thank you very much for your attention.